So last time we created a model like this, and did we talk about defining the load combinations? Janit, did you talk about all these combinations?
Yes, sir.
All right. Okay. Right. So then I also said that, if you are modeling the piles, then we'll need some kind of restraint at the ground level. Otherwise, the model can become unstable. So today we are going to see how the foundation can be modeled. So we'll first look at the theory part. So we can have different types of soil. So mainly can be divided into clay soils and sandy soils. So when you have clay soils, we know the clay soils also we can get SPT value. We can get a SPT value, and so based on the SPT value, we can actually define it as very soft soil. If the SPT value is less than 2, it's a very soft soil. If the SPT is between 2 to 4, it's a soft soil. So these two can be considered as very weak soil. Then SPT is between 4 to 8. We might say, it's a weak soil, but a firm soil. Whereas, if you have a clay soil and you are getting a SPT between 8 to 15, then you can see it's a reasonably strong soil. Maybe the bearing capacity may be around 60 to 75 kilonewtons per meter squared. And then if you get a SPT value of between 15 to 30, then it will be a fairly hard clay soil. That means, although it's a clay soil, it's fairly stiff clay soil. So when you know the SPT value, when the bow log is given, then you can actually see the SPT value for each layer. And also you can see the type of soil. So if it is say sandy clay, it's a clay soil. And and also in addition to that, you can get another type of soil that can contain both sand and clay. And that is the laterite soil. So laterite soil also contain a reasonable amount of clay. But you can also have another form of laterite, which is fairly strong laterite, where you might have less clay and more sand and gravel. So you can have different types of soil. So when you know the type of soil, our intention is to find the spring constant that we can use to represent the resistance given by the soil in the horizontal direction. So that is the horizontal subgrade reaction. So we are trying to see what is the horizontal subgrade reaction. And when you know the value of SPT, you can actually find the undrained cohesion. You can find the undrained cohesion. And undrained cohesion is given by a chart like this. And you can see the it's reasonable to say the undrained cohesion is about 4.5 times N or 5 times N. And then when it comes to the subgrade reaction, it is a function of elastic modulus of soil and the width of the member that we are going to model. So if you have a 1 meter diameter pile, then it's B is equal to 1. And nu is 0.3. So 1 minus nu squared is about 0.9. So generally we consider this particular parameter as 1. And then if you know the elastic modulus of soil, then we can find the subgrade reaction. Elastic modulus will be in kilonewtons per meter squared. So once you divide it by B, you get the answer in kilonewtons per meter cube. And then if you want to find what is the spring constant is given in kilonewtons per meter. So that means, you have to multiply whatever the Ks value by the area represented by each spring. So the area represented by the spring will be the height between two springs multiplied by the width of the member, So here you will see to find K's value, we divide the elastic modulus by B, and then we multiply it by B times H. So you can simply say the elastic modulus, the spring constant will be elastic modulus multiplied by the vertical spacing of springs. Because to find Ks, we divide Es by B, and then we multiply it by the area, which is B multiplied by H. And H is the distance between two consecutive springs. Then it's also important to find what is the value of the ratio between elastic modulus and undrained cohesion. And it is given by, experimentally it is found like this. It varies with the over consolidation ratio, and also another important parameter is plasticity index, which is liquid limit minus plastic limit. So we have to get a value. So if the SPT values are very low, then we can say the plasticity index is greater than 50. Whereas, most of the good soils, you will find plasticity index is less than 30. And if you are in doubt, you can even consider plasticity index is between 30 to 50. And then based on that, you can find a ratio for ES over CU. So when you have a reasonable estimate of the CU value, you can find the elastic modulus of soil. You can find the elastic modulus of soil. So basically, it's okay to go with ratio like over consolidation ratio like 3 to 5. And if you think during the history of this location that this soil has been subjected to very high stresses, then you can even say the over consolidation ratio is greater than 5. But it's usual to use a value like this, and then which means the over consolidation ratio is between 3 and 5, and then you can use some of these values to find the ratio between ES and CU. And so that is for the clay soils, which means for clay soils we can find the horizontal spring constant. So we'll take an example, and so if you look at, so let's take a typical bowlog, but this is a bowlog at a place where the soil is reasonably good, where you have something like, let's say, for the first 4 meters, we are having fairly weak soils, a sandy clay, having SPT of only 5. And then 4 to 8 meters, we'll consider that 4 to 8 meters, we'll consider that the SPT value is about 12, and it's a laterite soil, but not a very strong laterite soil. It may be a laterite soil containing certain amount of clay. And then we go for 8 to 12 meters. And then if you look at SPT value, we say the SPT is about 20, and we are having laterite soil. So so let's assume that we are having this type of clay soils. So if we take this sandy clay where the SPT is 5, then we can first find the undrained cohesion, and undrained cohesion will be 4.5 times 5, 4.5 multiplied by 5, so you get 22.5, 22.5. And if you look at the table, and you see that we can say that we are having very weak soil with over consolidation ratio of 3 to 5. So we consider that the plasticity index is, so we have to think about the plasticity index, and that it's a sandy clay, but SPT value is very low. It is only about 5. So the chances are that plasticity index may be less than 50. But if you want to be conservative, you can even assume that the plasticity index is more than 50. But if you have already done a test and you have found the plasticity index, and if it is less than 50, then you can use 200. And if you haven't done it, then you can check, you can use this value. So you can see when you have clay soils, it may be a good idea to find the liquid limit and plasticity limit as well. When you can request this liquid limit testing also done when you have clay soil samples, so that you will be able to make a reasonable estimate of the plasticity index. Based on that, you can decide the ratio that you are going to use. So basically we'll use 75 for this particular soil. So if you are using 75 for this ratio, then we know the CU value as 22.5. So we can find the ES value as 22.5 multiplied by 75. So you see these are very conservative value because we are using the minimum values for the minimum value for this ratio. And so you get 1687, 1622.4.5 into 5 into 75. The answer is 1687.5. 1687.5. So so based on that, I can substitute here 1687.5, and this influence factor is 1. 1 minus mu squared is 0.9, that's about 0.9. If I take that also as 1, then you can see the width of the diameter of the pile is 1 meter. So because the diameter of the pile is 1 meter, you see the Ks value is equal to ES is equal to ES, and that is 1687. So you can find if you have clay soils, for each clay layer of different properties, you can find a value for the spring constant, horizontal spring constant. Then the other type of soil that is available, before that, any questions on finding the the horizontal subgrade reaction flow clay soils? Any questions? Then we look at sandy soils. In sandy soils, the horizontal subgrade reaction is not constant. It is actually increasing. You have sandy soils, then it's increasing. Then the question is, sometimes, now you have to decide what do you mean by sandy soils. And in reality, sometimes you can encounter sandy soils directly. Sometimes, you can encounter something like this. So you might encounter something like completely weathered rock. Completely weathered rock. You might encounter something like completely weathered rock. And when you have completely weathered rock, then it's better to consider that as sand, because what happens is when the rock disintegrates, finally it will form, coarse sand and gravel type particles before it decomposes to the level of clay. So even that, it's most likely to be of sandy nature. So we'll consider that as sand for our calculations. So in sandy soils, what happens is the horizontal subgrade reaction is a function of the depth. It's a function of the depth. And to find the value of NH, we have to see what is the type of sandy soil we are having. So basically, if you have it again is based on the SPT value. And based on the SPT value, you can select a reasonable friction angle. And then when you know the friction angle, then you can work out the relative density. You can work out the relative density. And based on that, you can define whether it's a loose sand or very loose sand or medium dense sand or dense sand. So basically, you can work out the type of soil that you are having. And based on that, when you decide the kind of relative density, here, we can make use of this particular curve. And this is the relative density. And then this is the NH value. So if the relative density is about 60%, when you come this way, you can see NH value is little over 20,000, little over 20, but you can see it's in meganewtons per meter cube. So if you convert it to kilonewton per meter cube, then you will get 20,000 here, 22,000 here. So you get 22,000 here. So you get a value of 22,000. So if you get a value of 22,000, so every 1 meter height, the soil subgrade reaction due to sandy soil will increase by 20,000. Every 1 meter height, spring constant will increase by 20,000. Every 1 meter height, the spring constant will increase by 20,000. So you will see that it's not constant in the case of sandy soil. It will increase with the height. So based on the SPT value, you can work out the type of sandy soil available. And then what you do is, for every 1 meter, you will increase the value by the quantity that is calculated here. So NH, you know the value of NH, then you can work out the variation of spring constant. Then the other type of soil that we encounter is not real soil, it is the rock. So when you have a bowlog, you know, below the completely weathered rock, you can get even sometimes weathered rock. And weathered rock may be slightly larger particles. And below the weathered rock, generally when you say completely weathered rock, it's more sand. And when you say weathered rock, it can be sand and gravel mix. Then what you do is you drill further and then you encounter what you call fractured rock. So the rock is there, but it is fractured. And in fractured rock, when you take the sample, you will find the RQD value is very low, something like 10 or even 0. And core recovery is also low, which indicates that the core is not there everywhere. So sometimes you get rock, sometimes you get a mix of gravel, sand and clay as well. Then you go further down, and when you do unconfined compressive strength test, that is, you take the rock sample and subject it to unconfined compressive stresses, then you simply test it in compression. Then you will find the unconfined compressive strength is fairly low in fractured rock, and it can be higher in basement rock. And based on this, we can actually work out the type of the elastic modulus of the intact rock. So if the rock is not very strong, the elastic modulus may be slightly higher than the elastic modulus of concrete, something like say 25 to 30 kilonewtons per meter square. Kilonewtons per millimeter square, 20 to 30 kilonewtons per millimeter square. Whereas if you have a fairly strong soil, a strong rock, something like, unconfined compressive stress of about 40 or more. When you test rock samples, you get sometimes you get fairly high values. And then you might say the elastic modulus is around between 30 to 40, or even very strong rocks, it can even go up to about 50 kilonewtons per millimeter square, 50 kilonewtons per millimeter square. So you might look at these values, and then you have to work out the elastic modulus of intact rock. So elastic modulus of intact rock has to be obtained, and then if you know the elastic modulus of intact rock, ER, then this EMO-ER ratio is given in this chart, and you can see if the RQD is very low, and then you will get something like 0.01 for the ratio. So if the elastic modulus of intact rock is 20 kilonewtons per millimeter squared, means 20,000, 20 into 10 to the power 6, 20 into 10 to the power 6 kilonewtons per meter squared. And when you multiply it by 0.01, 20,000 multiplied by 0.01, you'll end up with a value like 200,000. You'll end up with a value like 200,000 kilonewtons per meter square. You'll end up with a value like 200,000 kilonewtons per meter square. So basically what you know is, if you know the value of RQD, if you know the type of rock available, you can always find a horizontal subgrade reaction for rock as well. Horizontal subgrade reaction for rock as well. So let's see how to actually make use of this in practice. So now we know how to calculate the values, and if you look at the values, I have actually calculated some of those, and so for the very weak soil, I will get a ES value of about 1,675. For the other soil, that is, the SPT value of about 12, I will get a value like 54. And here you can see and for this, I have actually considered KSO KU ratio as 200, considering that because this is a fairly reasonable soil with SPT of about 12, I will consider that, it's the plasticity index is between 30 and 50. And actually, if you do a test, sometimes you will find that the plasticity index is less than 30. So in that case, you can even use a higher value like 400. Then you will end up with a horizontal subgrade reaction of 10,800. 10,800. So if you are dealing with a big project, it's always good to request the values of plasticity index as well, because then you can always work out the horizontal subgrade reaction. So then we have a laterite soil of about 20, giving an undrained cohesion of about 90 and a plasticity index about less than 30. Then you will get something like ES of 36,000. Just one moment. Yes, I'm back again. And also, there might be a power failure around 12 o'clock. So I will, as soon as if the power failure happens, I'll switch back to the dongle. So give me 1 or 2 minutes around 12 o'clock if something goes wrong, right? So basically, so you can see the values that we have calculated, and you can see for each soil layer, we can work out the undrained cohesion, and based on the plasticity index, you can work out the ratio, and based on that, you can work out the ES value. Based on that, you can work out the ES value. And then for rock, you have to work out the ER value. And then based on that, again, you can work out the spring constant. And here for sandy soils, you will see that, the spring constant is going to vary linearly with the height, and every 1 meter it's going to increase by a certain amount. So I have actually considered that this value is 30,000 or 35,000, 30,000. So 30,000 every 1 meter it's increasing. So 30,000, 60,000, 90,000 and 120,000. So it will increase. So those are the values. So using this information, you can actually calculate the different spring constants. And then what we do is, in the model, I'll save it as A. And first thing I have to do is I have to remove all these links, and remove all these links. And then what I do is I can divide the piles. I will consider that, I'm applying a spring constant at every 2 meter interval. So I can divide it into 2 components, 10 components. So here you can see now the piles are all divided at 2 meter. So every 2 meter height, you get a spring. Get a spring at every 2 meter height. So here you can see 18, 16, 12, and so on. So to apply the springs, the first thing is, you have to go to 3D view and select one of the views and select selection. So you can select spring level, and then we have to see how much, what we apply for the spring constant. So we say assign, joint, spring, and we can apply it in the global direction, X and Y directions. And the spring constant, if you look at the top level, it is constant and 1675 kilonewtons per meter cubed. So if you have that value 1675 multiplied by each spring is representing a height of 2 meters, So over the first 4 meters, we have a spring constant of 1675. So this spring is actually representing the soil from 2 meters. So this is 1 meter, 2 meter. So 1 to 2 meters and 2 to 3 meters. So in this area, we have a spring constant of 1675. So I have multiplied by 2. So it's actually 1687.5. So I'll consider it as 1675. So once I multiplied by 2, so I'll get 3350. And the value of 3350. So I can apply the springs like that. Then I have to consider the next level. And that is, at 4 meters. So when you look at the soil profile, 3 to 4 meters we get sandy clay. 4 to 5 meters we get laterite soil. For the laterite soil, we calculated the spring constant as 10,800. And for the sandy clay, we have a spring constant of 1675. So what we do is, we can add those two and divide it by 2, take the average value, and then multiply it by 2 again to represent the height. So the spring constant that we get here will be, when you select the spring here, in this area it's 1675, this area 10,800. So over this height of 2 meters, I have to allocate the average value. So I'll allocate an average value of 12,475. So similarly, I can apply the spring constants for all these different layers. And then it will be possible for me to represent the soil stiffness as a series of springs and then see what the type of bending moment that would be transferred onto the piles as well. So that's how you will model the soil. And there might be a disconnection of the link. So shall we take a break now and start at 1:30 after lunch, because I'm having a power cut until 2 o'clock. So around 1:30 I should be able to manage with the battery for about half an hour. So we'll start at 1:30 and use the second link to join, and I'll show you how to model further with things like transfer plate and so on after the break. Okay.